Welcome to Einstein's Mechanics. In today's episode, we are going to look at the N-type and the P-type semiconductors. So basically, we will talk about semiconductors, how current is generated through them. So we are going to talk about electron and hole current in a semiconductor. How do they come about? So first part, we have what we call the electron current. And we also have a current we attribute to what? A hole. So we call that as hole current, and this is electron current. Remember, we use electron to represent the negative charges, and the absence of an electron creates a hole, which is also what? A positive charge. So how do we get the electrons to produce the current? This is a diode, as we can see here. First, it is in its intrinsic state, meaning the pure state, which means there is no doping, no foreign material has been added. So we are saying when a voltage is applied to a piece of intrinsic silicon, mostly we use silicon for our analysis. Well, we can also use germanium, but when we compare voltage generation and we did an analysis comparing germanium to silicon, and silicon is more preferable. Are we okay? So when we apply voltage to a silicon, it generates free electrons in its conducting or conduction band, and these electrons are free to move in the crystal structure, which are easily attracted to the positive end. And this movement of free electron is one type of current generation in semiconductive material, which we call the electron current. So this is a diode. We can see it over here, which is in its original state. So if we apply a voltage, say V, across the diode, we can see that this is the positive side and this is the negative side. Electrons, which are the negative charges, will be pulled towards the positive end. And as an electron is moving, it is going to create a hole. So that hole also gives room for one electron to occupy it, and you will see a net movement of electrons towards the positive end. So this movement of electrons is going to create a current. So we know that the movement of electrons creates current. So this is the general overview of how electron current is created in a diode. As we apply the voltage, they become excited and they move towards the positive end. So this is going to create a hole by its absence to be occupied by the other, and this is going to occupy the hole created by the other, and this movement is going to create a current, which we refer to as electron current. Are we good? So now let's also look at how the hole current is going to be created. Remember, this movement of electron is in the conduction band. The conduction band. The electron current is created in the conduction band. Are we okay? Let's look at how the hole current is also created. Now, electrons remaining in the valence band are still attached to their atoms. So we know that once the electrons gain much energy, they escape from the valence band to the conduction band, leaving behind the less energetic electrons. Are we okay? And let's say if we have 20 electrons in the valence shell, and we are getting 10 of them moving to the conduction band, meaning now we are going to have 10 electrons and 10 holes being left in the valence band, right? So this type of arrangement is going to explain how the whole current is created. So here it says electrons remaining in the valence band are still attached to the atoms because now they do not have enough energy to move into the conduction band and are not free to move randomly in the crystal structure as the free electrons do. But however, the valence electrons can move into nearby holes. Remember, now we are having 10 electrons, 10 holes. So meaning they can move from one hole to the other with little energy. We are still talking about semiconductors, and we saw that the gap between the valence band and the conduction band is not as wide as in insulators, but there's a gap, right? So it will need more energetic electrons to cross that gap. So here, the less energetic electrons are still left in the valence band, but the energetic ones has moved from the valence into the conduction, leaving behind holes. Are we good? Now, these holes can be occupied by the leftover electrons as they move from one hole to the other. Even if the electron is moving from its position to a hole, it is going to create another hole when it leaves. Are you okay? And this movement, although it is electrons moving, we attribute this current generation by the movement of electrons from one hole to the other as the whole current. Because the idea here is that it is the presence of the hole where these electrons will occupy is creating the current. Remember, when we are saying electron current, they are just free in the conduction band moving around to create the electron current. But with the whole current, it is the absence of the energetic electrons creating the holes. This ability is going to generate the current. Are we good? So let's look at the diagram here. We have from position 1 up to position 6. It can best explain this whole current. So here we are having a free electron leaves into the valence shell. Are we okay? So now we have an electron which is moving. It is moving. It is going to create a hole because the absence of an electron creates a hole, right? And the two, a valence electron moves into the first hole and leaves the second hole. Actually, this one is leaving into the conduction band. Are we okay? All right. Or even if it is moving into a different position in the valence band, it is going to create a hole. So this hole created is going to be filled by a second electron. That second electron is also going to create another hole by its movement. That hole is going to be filled by a third electron, creating another hole in the atom, and they will begin to fill themselves. If you create a hole, a different electron will fill. Do we see the arrangement? All right, so this movement of electrons occupying the holes created by the other is also creating a movement of electrons to cause a current. Although we may say this current is still electron generated, we give the credit to the holes, calling it the whole electron or the whole current. Are we okay? Alright, so this is how electron current and hole current is explained. That's very simple. Let's look at how temperature affects the resistance of materials, both conductors and semiconductors. Are we okay? So we are looking at a graph of resistivity or the resistance to temperature. Are we okay? And here we are saying the resistivity of insulators and semiconductors decreases with increasing temperature due to thermally generated electron hole pairs. So for insulators and semiconductors, as you increase the temperature, so this is for semiconductors, I'm increasing the temperature, but you see that the resistivity is decreasing. Are we okay? And for insulators too, if you increase the temperature, the resistivity is also decreasing, but that is not as sharp as the semiconductors. And the reason why this is happening is that for insulators and semiconductors, if you increase temperature, you are going to give energy to the electrons to move, right? To move from their valence band. I still want to explain. So this is the conduction band, this is the valence one. So let's say this whole thing is a semiconductor material or atom, or we have an insulator atom. Now I am applying more heat energy. So we apply heat energy to the atom. The electrons in the valence band or shell are going to gain energy. So they will try to move over. Are we good? So as they try to move, by the idea of how we explain the electron and hole current generation, there's going to be what? Current produced, or they are gaining energy to produce current. This is going to reduce the resistance of the material. Are we good? But when we look at temperature versus resistivity for conductors, it is quite different. We can see that already it is starting from a point here and it is linear. It is increasing. Do we see that? So the temperature of solids increase, or when we increase temperature, it is also going to increase the resistance of conductors. Are we okay? And this is also due to the interfering of what? The flow of electrons. So for example, when we take the copper or the copper wire, you see this is a pure conductive what? Material where electrons can move freely. But if we increase temperature from say 20 degrees Celsius to 40 degrees Celsius, so let's say at 20 we are generating, or the copper is able to conduct 10 amps. So at 40 it is going to conduct what? 5, because now its resistivity is what? Increasing. And this is due to the ability of interfering the flow of electron. When we say the interfering of flow of electron, what we mean is that for a conductive material, let's say this is a conductive material, the electrons are free to move and there are plenty of them. So a little increase in temperature will still make them more energetic, trying to move to a different band. But remember, we are only ending at what? The conduction band. So there's nowhere to move again. So they'll try to collide with each other, and their smooth movement will be what? Restricted. So as their movement is restricted, it is going to what? Reduce the work done. What we want to achieve is not going to be achieved. So at the end of the day, instead of us to gain the 10 amps current, it is going to reduce. Are we good? And as they collide, they are going to cause vibration in the atom, causing a decrease in current. So it is not advisable to increase the temperature of conductors, because it is going to decrease the flow of electrons. And when we talk about the insulators and the semiconductors too, although if you increase the temperature, you are decreasing the resistivity, but you have to also take care. If you continue to increase temperature, at a certain point, insulators, they will begin to what? Melt. So you will not even achieve that current you want to achieve. Do you understand? So you should be mindful in increasing temperature for insulators and conductors, or insulators, semiconductors, and conductors. Once you have the idea of how temperature affects their resistivity, you'll be able to do it in a controlled manner. Are we good? Now let's look at the N-type semiconductor and how to go by them. So we have two types of the semiconductor. We are going to talk about the N-type and the P-type. N-type representing what? The negative type. So that is negative type. And when we talk about negative type, we mean electrons are dominating electrons because they are the negative charges. It's a simple analogy. Are we okay? So here to achieve the n-type or to use the n-type to create current, what do? We say to increase the number of conduction band electrons in pure silicon, which is a silicon which is not doped. Very good. We use a pentavalent impurity and we add it to it. So first, before you achieve the n-type, remember the n-type is what? A doped. It is being what? Doped by what? Impurity. So first you pick a pure silicon and you dope it with a pentavalent impurity or atom. And when we say pentavalent impurity, we are referring to atoms with 5 valence electrons. So when you fill the electrons in the shells, you are going to get 5 at the outer shell. Such atoms, we can have phosphorus, we can also have antimony, we can also have bismuth as such atom with 5 valence electrons. So we pick any of these atoms with 5 electrons in their shells and we add it to our silicon atom. Remember, the silicon is what we are trying, is the semiconductor here, or the intrinsic what? Semiconductor we are trying to dope. So we pick the silicon, we add any of these atoms to that. Since silicon is having 4 valence electron and this pentavalent impurity is also having 5 electron, when we bond them, remember covalent bonding, each of them, the 4, they are going to pair with one of each pentavalent atom, as we can see in the diagram here. Each of the silicon, this is the silicon, this is silicon Si, is going to bond with one of electrons in the, so here we are using the antimony atom. Are you okay? So that, so let's say this is 1, this is 2, 3, 4, and this is 5 because it is 5 electrons in its outer shell being bonded by 4 silicon. So it is going to be left with 1 free electron. Do you see that? So this free electron is not involved in the bonding. What happens then? It is going to gain energy, then try to leave the conducting band or try to leave the valence band into what we call the conduction band. So imagine adding a lot of this impurity, adding a lot of the antimony impurity. It is going to generate, each one you add is going to generate 1 electron. This is going to, so if we add 20, we are going to get 20 electrons in the conducting band. And these electrons are free to move, going to cause the generation of what? Current. Are we good? So it is done in a controlled manner. If you want to generate large amount of what? Current, you know how to go by it. So if I want to generate 40 amps, maybe I will need 20 of what? The impurity. So here, if I want to generate, say 20 amps, then I have to control the impurity I'm adding. Say, let's say 10 of the what? Impurity atoms. So it is not just done, we control the amount being added so that we can get what we want to achieve. So this is the basic explanation. So always, if you want to achieve an n-type semiconductor, you add a pentavalent what? Impurity, an atom with 5 valence electrons, such that after bonding with the 4 valence electrons in the semiconductor, it is going to be left with one of the electrons to move into the conducting band to create what? Current. Are we good? Now let's look at how the p-type is also formed. So now we know that the n-type is due to one extra electron left. What about the p-type semiconductor? To achieve a p-type semiconductor, what we have to do here is that first you must get your intrinsic silicon, which is the pure state what atom, to create your semiconductor current. We pick the original silicon, then we try to dope it with a trivalent impurity. Now, trivalent impurity means it has 3 electrons in its what valence shell. Are we okay? So there is 3 valence electrons, and such of these atoms include the boron atom, the indium, and the gallium atom. They all have 3 valence electrons. Remember, the silicon that we are going to dope it already is having 4 electrons, right? So let's look at the diagram. This is boron, where we are going to dope it with the silicon. So the boron is having 3, 1, 2, 3. Are we okay? In order to complete the covalent bond between the 4 silicon atoms, boron is supposed to have 4, right? But here it is having 3 of them. So meaning this first silicon is going to bond with one of boron's electron to complete its configuration. This is also going to complete it. This is going to complete. But this part needs one more electron to complete it, meaning there is a hole created here. It needs an electron. It is a hole created. Are we good? So this hole creation, or the hole available, is going to expect that the electron should fill it. Are we good? So now nearby electrons are now going to move into this hole. And as they try to move into this hole, there will be another hole created. Do we see that? And since there is a hole created to cause the electric or the current generation, this is going to finally give us a p-type, a hole type. Are we good? We know that the holes, they are the positive. We attribute the positive terminal to the holes, right? So since there is a hole created for one of the silicon atom, then a p-type is what? Created. Very simple. There's always one more electron to complete. So if one more electron is needed, meaning a hole is present, giving it the positive type. So the p-type is caused by what? Trivalent impurity, whilst the n-type is caused by what? Pentavalent impurity. This is leaving the hole. This is also sending an electron. Are we good? So mostly what we call the pentavalent, we call them as what? Donors. We mostly call them as donors because they are going to donate an electron into the valence or the conducting band. But for the pentavalent, we call them, or the trivalents, leaving the hole, we are going to call them as acceptors. So this will be acceptor and this will be a donor. It needs one more electron to complete the hole. So it is now accepting. Are we okay? So this is a brief explanation of how the p-type semiconductor is formed. The n-type semiconductor is also formed. So one more thing. P-type means there are more holes. N-type means there are more what? Electrons. So the net effect of the n-type is what? Negative. The net effect of the p-type is what? Positive. Thank you for watching this episode. Please subscribe to the channel, drop your comments, and check out for the next episode.